Hi guys, today I'm going to present a video on design of singly reinforced beam by using limit state method of design. So please kindly subscribe to Civil Learn for more videos. So this is the problem which we are going to design today. This is the rectangular reinforced concrete beam section which is simply supported on masonry walls of 300 mm thick and 5.5 meters apart, that is center to center distance, to support a uniformly distributed live load of 15 kN per meter and a uniformly distributed dead load of 10 kN per meter exclusive of its self weight using M15 grade concrete and Fe415 steel. So in this case the center to center distance is given, so directly we can take the effective span of 5.5 meters. So assuming the effective depth of the beam small d is equal to span divided by 10, that is effective span is 5500 divided by 10, we will get 550 mm. In this problem we don't know the breadth of the beam and depth of the beam, so we are assuming the span to depth ratio as 10 here. After calculating the small d value, assuming the effective cover as 50 mm, so the total depth of the beam is equal to 600 mm. Then after finding out the total depth of the beam, calculate the width of the beam, that is B is equal to capital D by 2, that is equal to 300 mm. Loads. First of all, we have to find out the self weight of the beam, that is equal to width of the beam into depth of the beam, that is total depth of the beam into unit weight of concrete, that is equal to 4.5 kN per meter. In this case the self weight of the beam is exclusive, so we have to add the self weight of the beam, and dead load is equal to 10 kN per meter, live load is 15 kN per meter. So sum of these three is equal to total load, that is 29.5 kN per meter. After getting the total load, this is known as service load, we have to calculate the service load into factor load by multiplying with partial safety factor of loads, that is 1.5 into 29.5, we will get 44.25 kN per meter. After getting the factor load, calculate the factored bending moment. So the factored bending moment formula is WL square by 8, as the beam is simply supported and the load is uniformly distributed load. The factored bending moment formula is WL square by 8. By substituting the L is equal to 5.5 and W value, we will get 167.32 kilonewton meter. After getting the mu value, calculate the mu limiting value. Here we can do two types, that is by calculating mu limiting we can compare mu and mu limiting. If mu is less than mu limiting, then the section is under reinforced, but in this case I am checking the depth of that particular beam, whether whatever we provided is safe or not. So mu is equal to mu limiting, that is 167.32 into 10 power 6 is equal to 0.138 into FCK value is M15, so into 15, to B is equal to 300 and D should be unknown. Then find out the D required, that is 519 mm. So D required is less than D provided, hence whatever the section we taken is safe. So finally provide 300 by 600 mm beam of rectangular section. So the section is under reinforced. So for under reinforced section, for calculating the area of steel, we will use this formula, that is mu is equal to 0.87 Fy AST into 1 minus Fy AST divided by FCK BD. By substituting the mu value of 167.32 into 10 power 6 is equal to 0.87 into Fy value is 415, AST we should find out, and D is equal to 550 into 1 minus 415 into AST by 300 into 550 into FCK 15. By solving this equation, we will get AST is equal to 1219.17 mm square. Whatever the problem we designed, it should satisfy the minimum AST values and the maximum AST values. So first of all, we have to calculate the minimum AST, that is AST by BD is equal to 0.85 by Fy. By substituting the BD value and Fy value, we will get AST minimum of 350 mm square. So the minimum steel required for that particular cross section is 350 mm square. Here we got 1219.17. So the section is safe. And calculate the maximum steel, that is 4% of gross cross sectional area, that is equal to 0.04 into small b into capital D, that equal to 4 into 100 into 300 into 600, so that is 7200 mm square. So this is the maximum steel required for that particular cross section which we assumed. So whatever the steel we designed is within the limits of minimum and maximum. So assuming the diameter of the bar of 20 mm, calculate the number of bars. N is equal to 1219.17 divided by pi by 4 into d square. Here d we are assuming 20. So by substituting the values, we will get N is equal to 3.88 numbers. So provide 4 numbers of 20 mm diameter bars as tension reinforcement. So whatever the AST provided is equal to 3.14, that is pi by 4 into t square into number of bars, that is 4. So that is equal to 1256.637 mm square. So AST required is lesser than AST provided. So finally draw the section with the reinforcement details. That is, width of the beam is 300, total depth is 600, and effective depth is equal to 550 mm, and 4 numbers of 20 dia as tension reinforcement, and 2 bars of 10 mm diameter as anchor bars, and the steps are provided in this beam. So in the next video we can see what is a doubly reinforced beam and how to analyze the doubly reinforced beams and how to design the doubly reinforced beam. So please kindly subscribe for more videos. Thank you.